All right, so welcome back to DSP. And let me remind you that next week will be holiday time, so there will be no class meeting the entire week. Next week we will not meet, but then the week after that, it will be our first midterm. And the coverage will be from the beginning of the semester until today's material. So today I believe we can finish this lecture. So your midterm will cover from lecture 1 to lecture 6. Any question regarding the midterm? And tomorrow we have I gave you last year's first midterm, so you can take a look and see kind of the level of difficulty. 难度大概到哪边? Level of difficulty should be around about the same. But the questions will not be the same. Right? The level will be about the same. But anyway, so today we continue to study this quite important topic, linear difference equations. And we emphasize that the coefficients we are using there are all constant, okay? Time invariant coefficients. So linear difference equations, as we see them, they give us an implementation of a causal linear system, which is time invariant, so it's LTI, linear and time invariant, okay? And so in this course, in my class, I focus on using linear difference equations in a causal manner, causally. So remember the definition of causal system, it's about the impulse response, right? The impulse response should be all zero before time zero. Nothing will happen before the system receives any input, okay? So we limit our focus to the usage of linear difference equations in a causal manner. So last time we spent a bit of about 10 minutes. We went through this definition. So let's take a look again. So this is an equation with yn on the left-hand side, right? And on the right, we have linear combination of y, the output, the past samples, 过去的一些 sample, past samples n minus k, right? So from the previous sample all the way to the nth previous sample. We have a linear combination here, and the linear combination coefficients are all constant. The A and B, these coefficients are also constants. Okay, so take a look. That's the definition with yn on the left-hand side and everything else on the right-hand side. So you can also see this as one line of computer code. Seriously. Yeah, you can view this as one line of computer code, and this system can be implemented. 它可以被实现, or the system can be implemented. But otherwise, it's a rather straightforward definition. Everything's linear here. So just take a quick Z transform. So if we take Z transform on both sides of the equation, then this is what we have. Okay, not exactly this, but then Y should become big Y, right? Z transform. Y becomes big Y. X becomes big X. And we also apply a simple property that when we delay, if xn corresponds to big X of Z, then xn minus 1 as a signal which relates to n by shifting to the right with one sample. If we shift in the time domain by one sample, then the Z domain is rather simple to check that the Z transform becomes, there's an extra factor right here multiplied by big X. Okay, so if you apply this property to both sides, here we have the delay by k samples, right? Delay and k equals to 1 to big M. Okay, yeah. So you can just figure out that on the left, we will have y of z equals to something like summation minus a k, z to the minus kth power, and the k index remains the same with this limit from 1 to m. So that is a polynomial. That looks like a polynomial. So on the right, we have this term plus this other next term. again, with summing from 0 to big N, according to my notation. And bk, now delay is replaced by z to the minus k power. That's a factor that will appear right here. And xz, right? And the next thing here is to move everything that relates to yz, that has yz, move everything to the left. Then we have yz times a polynomial a of z equals to x of z times a polynomial. If we define this as a polynomial, if we define this as b of z, and it is in here we have a polynomial 多项式啊, we have a polynomial of z to the 1 over z, basically 1除以 z, z, or I say z inverse, z 的导数啊, z inverse 啊, z to the minus 1. Yeah, so we will stick to this notation in the entire semester and also in MATLAB. Okay, in the official documents of MATLAB, we stick to this notation. Ya equals to xb. It shows up a lot. We'll be repeatedly seeing this equation. Okay, so it will be nice to become familiar with this equation. Okay, yeah, please be familiar. Familiarize yourself with this equation, Ya equals to xb. Or we say yz divided by xz. Yz divided by xz equals to a go here, b goes on the top. Okay, bz divided by az, where both of them are polynomials of z inverse. So far, so good? But remember that y, what is y? Y is the output of our system. The output that our system produces while receiving the input x, right? And this is an LTI. Okay, so yz divided by xz is exactly the z transform of the impulse response, which is denoted as big H. Because we're talking about this, obviously this is a linear and time invariant system. Okay, yeah. So far, yeah, that's what this equation, this chain of 3 equalities are defined in this manner. Ya equals to xb, therefore y divided by x, which happens to be the system function, big H, should be equal to b divided by a, where both of them are polynomials. Okay, so far so good? So this is just in the z transform domain, we have this consequence. So with that, kind of a key question we can ask. First, given the coefficients, given these a and b coefficients, is there a way to calculate the impulse response given any such kind of difference equation? And the answer, of course, there is. Right? Okay, I will see how to do that. But then the next question is also important. When we write down any difference equation, sure, then we'll see in a moment that we can calculate the impulse response. But there's a general design rule, I say, 是一个设计上的原则 design principle, that when we design a difference equation in DSC, most of the time, in most applications, you want the system to be stable. We don't want the system to receive an input and the output goes to overflow. Okay, the output explodes to 10 to the 306 power. So we don't want that to happen, right? We don't like that. Yeah, we do not like that. So we want the system to be stable in the sense that when the system receives a finite input signal, or we say BIBO, when the input is bounded, the output should also be bounded. Okay. Some of you might be able to recall that this is probably something that you have learned in signals and systems. Yeah. As a general design principle, we don't want our system to be unstable. Okay? So to ensure that the system is stable, let's jump to the conclusion that we'll see that we need to check a property of A of Z. Okay? Consider A of Z being a polynomial, so it has roots, right? A of z is a polynomial of mth order, m 阶的多项式嘛。So in principle, it has m roots, right? And we require all the roots to be inside the unit circle. That's the conclusion. Okay, that's the conclusion. We want all the roots of A of z to be inside the unit circle so as to ensure that the system will be stable. Okay, and there's a reason we'll cover. These are the topics that we'll cover today. First of all, let's learn how to calculate the impulse response of any difference equation systematically. And second question is understand. We want to understand why this is case. It's all about A of z, okay? No requirement whatsoever for B of z. Just check the roots of A of z, okay? And it actually makes some sense. You see that here, A of z, if we go back one slide, what is A of z? A of z is kind of a feedback, you know? Producing the output and then the past output will influence the next output, the present output. Okay? So in a sense, this is a sort of feedback. The system produces an output and we store it, and then that output will influence the next sample. Okay? So this is feedback. So when there's feedback, we worry about stability. Okay? But in here, it does not affect stability. Okay? So but the coefficients here do affect stability. So that's kind of that also explain why in terms of when we analyze stability, we only check the roots for A of z. We don't worry about B of z. Okay, no worry about B of z. Okay, yeah. Anyway, so let's now the next. So those are like the general scope and formulation. We have z transform. We apply z transform to a difference equation, and now we have ya equals to xb. Okay? Any difference equation can be transformed to this equation in the z domain. Right? Okay, so next, in the next few slides, we will use Fibonacci sequence as an example. It turns out that Fibonacci sequence is the solution, the impulse response of a difference equation. So let's take a look. And this is the difference equation we're talking about. Okay? Let y be the sum. This is a linear combination of past samples, right? Linear combination of the two samples in the past. So that's this part. That's this part. Okay, that corresponds to that part. Plus our input. Okay, simply the input itself. No linear combination. So this is a pretty simple case with all the coefficients 1, 1, and 1. Probably a very simple example, right? So then our goal is to calculate the impulse response. Yeah. So by definition, what is impulse response? Impulse response is the system's response when receiving delta function as the input, right? So just by definition, we can write, okay, if H denotes, H 用 H 来记载啊，用 H 来表达。If H denotes the impulse response, then by definition, this is what's happening when the system receives delta as our input. The response should obey this equation, the original equation, with H being the output, delta being the input, right? So when the input is delta, the output is H. Right? So far, so good? So if we move one step further, then let's go to the Z domain. Going to the Z domain, we have this relation. What is H? Then H is 1 divided by that. This is B of Z, this is A of Z. Okay, so one or the other. So you can probably rather easily reach this conclusion that H of Z, in this case, can be written as B of Z divided by A of Z as a special example. Okay? So far, nothing's new, just same thing right here. Okay? So far, so good? We good? Yeah? Okay, so But then next step, I suggest that let's do a factorization. 做一下因式分解啊 factorization. Let's factorize a of z. A of z is a quadratic polynomial. 它是二次的，对不对 ？Yeah. So it has an order of 2, so we expect that it should have 2 roots. They might be the same root, which is not the case right here, but in general, a of z, if the order of a is 2, then we can further factorize this polynomial into this form. And please do note that a of z, the leading coefficient, 那个首次的这个什么 leading coefficient, 常数项的那个系数啊 the leading coefficient is always 1 in this entire formulation. Okay, please notice that this is a process. So 1 minus something. This is a1 coefficient, a2 coefficient. Right? It's a second order polynomial. In principle, it should have 2 roots. And this is the way we express the factorization. Okay? And the 2 roots being P1 and P2. Okay? Take a look. Yeah. So if this has not been, it doesn't look familiar to you, please let me know. Yeah. So this is the way we will, kind of my way of notation. Okay. Yeah. Second order polynomial, but the exponent is negative. It's a little tricky. We are more used to the kind of polynomial when the exponents are positive. But here, the exponent right here, 指数的部分的 exponent, -1, -2. So please spend some time to make sure you are familiar with this notation. Okay, yeah. But otherwise, this is nothing but factorization. Simply the relation between roots and coefficients. 跟与系数的关系啊 Yeah. So far so good. Yeah. Yeah. So in principle, we can do that. So where P1 and P2 are the 2 roots to this polynomial. So let's calculate P1, P2, shall we? Yeah. Right. So how do we calculate P1, P2? So basically we have 1 minus Z1 minus Z equals 2. This is my notation. Let me just copy it. Yeah, so basically P1, 2 is, if we call this is A, this is B, this is C, then we can apply the formula. P1, P2 is basically 2A at the bottom, my reference for E, plus or minus square root of B squared minus 4AC. Yeah, seriously, this is nothing but that. Yeah. It's nothing but that. Yeah? Okay, yeah. So equals to 2 times 1 minus B minus of minus 1 plus or minus B squared minus 4 minus, yeah, seriously, that's that. Yeah. This is nothing but applying this good old formula. Okay, yeah. High school math. So now we have the famous factor of 1 plus or minus square root of 5 divided by 2. The golden ratio. Some of you might notice this is that's P1 and P2, the 2 roots. Okay, seriously, this is what we need to go through. Okay, this one was one in our derivation. And remember, why are we doing this? Please be reminded that we are trying to calculate the impulse response. Okay, but somehow I suggest, or the textbook suggests, that we go through this factorization, 因式分解. We go through this factorization. That's a middle step, intermediate step right here. Okay, so let's follow this. So if you're okay to follow this, so far so good. Are we okay? Yeah, are we okay to follow this way of derivation? So this is a intermediate step, and then we have calculated both roots. Then the next Then the next trick has a name. Okay, the next trick. I said this really is a trick, but if you prefer, it has a name. The trick is called partial fractional decomposition. Partial fractional decomposition. And what is that? So remember that this is h of z, right? B divided by a, that's h of z. And h of z, we have shown that h of z, now h of z, we have shown that it is 1 minus p1z inverse. There is a factorization in terms of the product of two terms. Now, this is the product expression. 乘以嘛, just product. This is a product way of expressing h of z, but it can also, it has another way, another expression. Okay, so it turns out that any bz divided by az in principle, if the bz's order is lower than that of a of z, b 的阶数, if bz's order is lower than a, if b's order is lower than a, and in this case, indeed, this is B. B is zero order, right? A is second order, right? So B's order is lower than that of A. If that's the case, then we can rewrite, you can always perform this fractional decomposition into 1 minus P1 Z inverse, and there's a coefficient A alpha K that has to be determined. Let's call it alpha 1 right here, okay? And next, is 1 minus P2 Z inverse, and that's up. There is also a corresponding coefficient alpha to be determined. Okay, and this the fact that we can always write this, we can always find alpha 1 and alpha 2 such that the identity holds. Okay, this fact, the fact that we can do this is called partial fractional decomposition. Okay, you can always do this. Unless, okay, there's an exception. Unless A has a multiple root. 如果 A 有重根的话, situation will become more complicated, slightly more complicated, but let's not worry about it for now. Because in this case, we don't have multiple root. The two roots are different, right? One plus or minus square root of 5. So the two roots are different. So we don't worry about the situation for now. With the multiple root that can make our story more complicated. That complicates our story, but let's not worry about it for now. Okay, but this is the kind of the recommendation. Let's try to find. So let's just force the equality to hold, and then we attempt to find alpha 1 and alpha 2. Okay, where P1 and P2 have already been solved. We already know P1 and P2. P1 and P2 are these golden ratio. Okay, P1 and P2 are already known right here, but what's unknown, still unknown, is alpha 1 and alpha 2. So far, so good? So that's, again, the second intermediate step. One side, one step. Okay? All right, so let's follow the slide. This trick is called partial fractional decomposition. And if we are fortunate that AZ does not have any multiple roots and B's order is lower than that of A, then BZ divided by AZ can be further rewritten in the following form, where P's are the roots, which we have calculated, and the alpha coefficients need to be determined. As I will show that in the next slide. Okay. Yeah. So now let's do this exercise, okay? So as I show here, the exercise is how do we calculate alpha 1 and alpha 2 given P1 and P2. Yeah. And so let's do it. Okay, so I left one really blank page for you to use. But basically, let's work on the right. But basically, we have P1, P2 is already given, right? P1, P2, P1, P2. I've already calculated P1 and P2. Okay? So there are a few different ways, okay? One possible way is to just keep playing with this expression, okay? If the equality holds, then the bottom should be 1 minus P1 Z inverse. Let's put the two terms back together again. Put the two terms back together again. On top, what do we have? On top, we should have alpha 1 multiplied with that plus alpha 2 multiplied with that, right? Should I repeat? Yeah. I want you to take a look, right? So if we just keep playing with this expression, then going back to put these two terms together, then at the bottom, the denominator right here should be back in this expression, but on top, the numerator should equal to alpha 1 times 1 minus P2. I'm sorry, 2, the P2 right here, the inverse plus alpha 2 1 minus P1 Z inverse, which equals to that, okay? So far so good? Yeah. Now, this is one way. I'll show you another quicker way, but this is a more sort of naive, 比较天真 or naive. This is a nice word that we should all learn. 天真 naive. This is one naive way. The naive way. Naive. With two dots, okay? This is French. Yeah, it's a naive way, 天真的方法啊。The naive way is not bad. 不是要求啊，是天真。写好一点，天写成妖就不好啊。妖真啊。The naive way is to do this, okay? But what's next? Any suggestion? What's next? In this naive way? Because this is equality, right? So we can compare this expression with this expression. The bottom is already the same, but the top also needs to be the same, right? So we can say, okay, therefore from here we have two equations for alpha 1 and alpha 2. The first equation is the constant term alpha 1 plus alpha 2 must equal to 1, right? Yeah. So alpha 1 plus alpha 2 must equal to 1. And secondly, alpha plus minus of P2 plus alpha 2 plus minus of P1 must be equal to what? To 0, because on top right here, we don't have the Z inverse term. We don't have the Z inverse term, okay? So alpha 1, P1, no, P2. Is it P2? P2, right? Yeah. Plus alpha 2, P1 must be 0. So that's a naive way. We have two coefficients to determine, and then we come up with two equations. And you can solve the two variables with two equations. Okay, hopefully you can do that. Yeah, that's a naive way. In principle, it can be done. The P1 and P2 just look a bit ugly, with square root of 5, but in principle, this can be done. Okay, yeah. So I said this is a naive way. Okay, so far so good. Yeah. So if you're interested, you can work it out, okay? It will give you the solution. You can find alpha 1 and alpha 2 in this way. But the not naive way, the more professional way of finding alpha and alpha 2 is this other solution I'm going to suggest, okay? So let's try to see if there's a solution 2. So this is solution 1. And solution 2. In solution 2, ready? Are we ready? Yeah, so far so good? Yeah. So there's another way, a slightly easier way, okay? Yeah. Solution 2 is to focus on this equality, okay? Focus on this equality. Let me use another color. Solution 2 is to focus on this equality right here. And then let's multiply both sides of the equation by a factor. Let's multiply, for example, let's multiply both sides with the factor of 1 minus P1Z inverse. So let's do this, okay? The equality should still hold, okay? So as a result, if you do that, then on the left we have this term. On the right, what do we have? On the right, we have alpha 1 plus what? Alpha 2, 1 minus P1Z inverse divided by, just multiply both sides with this factor. That's our recommendation. The equality should still hold. Okay? And the next step, is to let this term is big and we want it to vanish. We want to make it disappear. Okay? All right, so that's the spirit. So next is to then consider Z equals to what? P1. Evaluate both sides by making this substitution. 代入 Making this substitution, let Z be P1 and substitute. Then what do you see? Then what do we have? You see what's going on? Right? If we just evaluate both sides of the equation at Z equals to P1, then 1 minus P2 divided by P1, right? Z equals to P1, okay? Equals to alpha 1 plus what? Plus this big term right here, but it's 1 minus P1, Z equals to P1, and at the bottom is not important anymore. But for the sake of completeness, I finished writing, okay? So what do you see? Did you notice? Are you noticing what's going on? Beautiful. What's going on is right here, this term vanishes, right? We make the term vanish. 我们让它消失啊 we cancel the term. We make the term vanish by evaluating both sides at Z equals to exactly P1. Okay, so that's a kind of more professional or sophisticated way. Sophisticated, 熟练的 This is a more sophisticated way of already finding alpha 1. What is alpha 1? Because now, what do we have? Alpha 1 is equal to that. Everything is known. P2 is known, P1 is known. There's no unknown right here on the other side. Okay, so that's a trick. Yeah. Okay, people in the back, can you see? That's a trick. Okay, I believe some of you might have learned this in engineering math or in the signal system, but this is a review. Okay, both are okay. I think both are fine. Okay, both are fine. But here, this is. So I say this is a more sophisticated way finding alpha 1. So let's just complete this. So alpha 1 is what? Alpha 1 is 1 divided by 1 minus P2 divided by P1 right here. Okay, that's a ratio. P2 is 1 minus square root of 5 divided by 2 divided by 1 plus square root of 5 divided by 2, okay? I'm slightly running out of space, but you know what I mean. So alpha 1 is that. And so with some further bookkeeping all the factors, you can figure out, okay, use your blank space. 2 is now gone. So I would multiply top and bottom with 1 minus square root of 5. Okay. So this is 1 plus square root of 5 minus 1 minus square root of 5. And on top, we have 1 plus square root of 5. And so the answer is what? Looks like my answer, at least, I will stop right here, okay? Yeah, let me just stop right here. I have figured out that alpha 1 is that. Right, not beautiful, yeah, it is a bit ugly, but I believe this is correct, okay? And it's both were fine, solution 1, solution 2, okay? And we are talking about, we're still in the middle of trying to find the impulse response, okay? We're stuck in the middle. This is the third intermediate step. Okay, so far so good. But yeah, just be patient. We can find alpha 1 and alpha 2. And in principle, you can also find alpha 2. So I will not repeat the process. I've done this at home. So you can also try it in your free time. Alpha 2, what do we have? Alpha 2 should be right here. Okay, so let me just copy everything to the left. So with a summary. Okay, so let's summarize. We have a system function. So let's summarize. We have a system function that's bz divided by a of z, which turns out we can perform partial fractional decomposition to write it as alpha 1 divided by 1 minus p1 z inverse plus alpha 2 divided by 1 minus p2 also z inverse, where p1, p2 is 1 plus or minus square root of 5 divided by 2. And we have figured out alpha 1 is that. Okay, let me take a look. Alpha 1 is that. We have the result for alpha 1. And alpha 2, okay, so I've done this at home. Alpha 2 turns out to be also in this form with 2 square. Yeah, so I'm trying to be careful. There's a minus sign, 1 minus square root of 5. Okay, yeah. So everything now is explicit. 每一样都已经写出来了. Everything is explicit. Yeah. We know all the factors, alpha 1, p1, alpha 2, and p2. But then what's next? The next is to understand that it turns out that each factor right here, these two factors have the same formulation, right? 长得蛮像, same formulation. Only coefficients are different. But then I suggest let's just force this sort of with a leap of faith. 信心跳跃一下嘛. With a leap of faith, let's just apply this identity. What is this identity about? It's just rewriting this term into an infinite series, into basically a power series. At least technically, this is my suggestion. Okay, technically, I suggest that let's rewrite this term which shows up in the partial fractional decomposition. That's that, right? And I'm missing a k, by the way. I'm missing a subscript. 下标忘了写啊. Please make a correction, okay? So right here, this is wrong. This should be alpha k right there, okay? Alpha k right here, alpha k also to the right, on the right-hand side of this identity, okay? So this is my suggestion. Rewrite this term into a power series. Into power series, and the beautiful, please note that in this power series, all the coefficients showing up right here is pk, pk squared, pk third power, and so on. And why is that? So why could this be true? And that's because as long as this factor has an absolute value that's less than 1, then the identity holds. So this identity holds under a certain condition. This identity will hold if and only if, okay? If and only if the absolute value is greater, z is greater than this p right here. But when this happens, indeed, this equation, we have the identity, okay? This is kind of the opposite way, the reverse way of summing a geometric sequence, right? 几何级数等比级数求和 It's the opposite reverse way of, if you look on the right, we have alpha, that's just simply a constant. But in here, in the parenthesis, 在括弧里面 in the parenthesis, inside here, we have a geometric series. 几何级数嘛 you have a geometric series, p z inverse, p squared z minus 2, p third z minus third, right? So it's a geometric sequence. Yeah. So as long as the common ratio, 这个公比，对不对？ As long as the common ratio has an absolute value that's less than 1, then that's a formula for the infinite sum. Okay. Here we're just using it in the opposite way. 我们是反过来用 That's a trick. Still, everything is trick right here. Okay. Yeah. We are still in the middle of trying to find the impulse response. But trust me, this is about the final step. So if you allow us, if you bear with me, if you just put aside your question for now, if you bear with me, then 受一下 If you bear with me, then we can apply this. Right? The trick is to apply this following identity, which is an opposite way of summing of an infinite geometric series. Apply this identity, and now we apply this to our system. Okay? Apply this to our system, then what do we have? That's P1, P2, alpha 1, and alpha 2 with a minus sign, okay? Yeah. So far, so good? So we can just directly apply this identity. And then this term becomes, that's the alpha part, that's alpha 1, right? This is alpha 1, this is alpha 2. So far, so good? And then P1 to the nth power times z minus n, okay? Plus 0, and similarly, we have P2 to the nth power times z minus n, and we just combine two terms. And we're almost done. Once you reach to this line, then the next is simply to notice this is h of z, now becoming a power series. 它是一个幂级数 power series 幂级数 It's a power series. Let me just introduce this term. I write it on the board. Power series. So now we have a power series h of z equals to summation of something, big thing, and from 0 to infinity, a big thing right here, and z to the minus n. So in general, anything with any function with this expression is called a power series. This is a power series, or in Chinese, it's called 幂级数. The power series expression of h of z with big thing inside right here. But what's the definition of h of z? The definition of h of z is summation hn z minus n, right? That's the very definition from the very beginning. H of z is defined as that. That's simply a definition, right? So now, by comparing the last two lines, okay? Please, if you go with me, comparing the last two lines, that's the very definition of h of z, now equals to this power series. And the only chance for the two of them to be equal, okay? The only chance for the two of them to be equal is for every coefficient right here. Each coefficient should be the same in order for the equation to hold. Otherwise, there's no way to hold. Okay, so that's just comparing the last two lines. Okay, now we have different expressions for the same function, so they ought to be. So every term has to be equal, and that's a kind of very basic property. Essentially, saying that you cannot have two different expressions. If two power series are equal, then every coefficient is equal. Okay, that is a very basic property in math, right? So therefore, now we have, by definition, h of z is the z transform of h of small h. But now, just after so many steps, we have h of z also equal to that. With inside we have the sum of two geometric sequences. Something like that. Therefore, h of n for every n must equal to that. 1 plus square root 5, that's the alpha part. P1, if you will, let's just explicitly write out P1 n power minus that times P2 to the n power. When n is greater than or equal to 0, because the summation index starts right here. Okay? And 0 when n is before time 0. Okay? H is an impulse response of a causal system right here. All right, so we're about on time. Okay, let's take a break of 10 minutes. So there are a lot of thoughts to digest. I agree. I acknowledge that. But let's come back and contemplate on our solution. Okay, when we come back, we contemplate on this solution. But let's take a break of 10 minutes.